Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 2.3.4, Similar Triangle Proofs. The first question is a pretty basic one, even though it seems pretty lengthy. It talks about Scott knowing that if two angles of a triangle are congruent to two other angles of another triangle, then the triangles will always be similar. But now he's being asked to prove if that statement is true. Well, basically, what we're going to do is we're going to name the triangles this, based on the diagram, and do we know anything else? Well, luckily, we have that triangle angle sum theorem, right? And so we know that the three angles in a triangle have to sum to 180. And if angle Q and angle U are congruent, and angle P and angle T are congruent, then angle R must also be congruent to angle V. So angle R must be congruent to angle V, and that's going to be by our triangle angle sum theorem. And so pretty easy answer for such a long question, but let's go ahead and move on to B. I'll be right back. And in part B, it says, Scott says, I think it will help if we can match up two of the congruent angles. So Eliana says, well, if the angles are congruent, that means that the rigid transformations will move one onto the other. So we're going to map angle P onto angle T. What Eliana is trying to tell us is that she's going to take this angle here and map it over here. That way the triangles fit inside of each other. And so when they talk about describing the sequence of transformations, let's go and type this out here. Oops. Basically, a possible transformation would be to translate point P onto point T. And then a rotation about point P prime so that point Q lies on side TU. Side TU. And point R lies on side TV. Now, without actually doing it, no one really understands exactly what I just said. Totally understandable. What's going to happen is the left triangle basically is going to be eaten by the right triangle. So at the end, what it's going to look like, and what you guys are supposed to do in class is you're supposed to use the patty paper that has traceability. And so what happens is you end up with a diagram that ends up looking like this. Let me just go and scroll down here. You're supposed to end up with a triangle that's supposed to look like this, where angle T is going to be angle P prime, right? P prime being the new angle P that we have just formed right here. And then from here, this is the small triangle, right? So this is PQR. So this is going to end up becoming Q prime and then R prime right here. And then the U is going to stay in place and the V is going to stay in place. So again, imagine the left triangle being eaten by the right triangle. So what type of angular congruence does this give us? Well, we know that the angle P and the angle T are congruent, so we know that we can just do one big angle right there. And then angle Q, which had the double tick, and angle U, which had the double tick, are also going to be congruent. So that's what your image should look like after you have let the right triangle be eaten, let the left triangle be eaten by the right triangle. So let's move on to part C real quick and let's see where this problem takes us. Part C says, what do the angle relationships in the diagram tell you about the line QR, which is the middle side, and the line UV, which is the bottom side? Explain. Well, we know that angle U, so we know that angle U is congruent to angle Q, and they are also corresponding angles. So what I'm going to do is I'm going to use this knowledge in reverse, and I'm going to say because the corresponding angles are congruent, that means, so again, remember these three dots means therefore, that means that QR and UV are parallel. So I just used the definition of parallel lines and their angular consequences in reverse, where I basically say, hey, if corresponding angles are congruent, then the lines must be parallel. It's the converse of the if lines are parallel, the corresponding angles are congruent. So hopefully that makes enough sense. Let's move on to part D. It says, Eliana says that that looks like the problem with the rubber bands. We can just dilate P prime, Q prime, R prime, and we'll have TUV. Sorry about that. That was my email. I'm going to cancel that. Let's see here. And Scott says, but we don't know the side length, so how do we dilate so that the vertices match up? Help them write a scale factor that will take point Q to point Q prime to point U if T is the center of dilation. And so it says it might help to start with numeric measures. And so why don't we go ahead and do that? So because you're supposed to be using the rubber bands on this one, what you end up finding is that the ratio of P prime, Q prime over TU is going to be 2/3. So, and that should make sense because of the fractional scale factor that would shrink the larger triangle onto the smaller triangle. So part E says Kendall is confused. Okay, I know that parallel lines stay parallel after a dilation. So if Q prime, R prime, and UV are parallel and point Q coincides with point U, then point R will coincide with point V. But my diagram doesn't look like Eliana's diagram. Will it still work? See Kendall's diagram at the right. Will the dilation you described in part D still work? Explain. Basically, to answer part E, and this is kind of an odd question here, and they're really trying to get you to think about how things are drawn. And it says the original diagram isn't, so because the original diagram isn't drawn to scale, we don't really know which triangle is larger. But for the diagram in the dilation to work, the ratio just has to be less than 1 in order to shrink PQR into TUV. So as long as your scale factor is less than 1, then you'll shrink then you will shrink your figure. So that should answer part E. Not really that pertinent of a question, but let's move on to the next question. All right, let's talk about this famous side splitter theorem here, where basically it says Janelle and Kamran are working on their homework together. For the diagram below, Kamran wrote the equation 4 over 6 equals 5 over 5 plus x. Is his equation correct? Explain, if needed, revise his equation, and then solve for x. So for this, I would highly recommend, whenever we see a triangle inside another triangle, split it up a little bit, right? Especially if we're going to solve for x here. So if this is E, A, and J, then this will be a 5 and a 4. And then the larger triangle is going to be J, L, and N. And this is going to be, it's not x here. Everyone's going to think it's x. It's 5 plus x, right? Because it's the whole shebang right here. And then the other side is not 2, it's 6. So let's see if Kamran is correct. It looks like he did compare corresponding sides. He did say 4 over 6 is equal to 5 over 5 plus x. So I think his equation is all good. Let's go and cross multiply this guy and solve him out. So 30 equals 4 parentheses 5 plus x. So if I distribute that in, 30 is equal to 20 plus 4x. Subtract 20 from either side. 10 equals 4x, so divide by 4, and x equals 5 over 2. Looks good, Kamran. Good job, man. Okay, so now Janelle says, wait a second, I accidentally did 4 over 2 equals 5 over x. So this is part B here. And I got the same answer. Check it out. So 10 equals 4x. So divide by 4. X equals 10 over 4, 5 over 2. Cool. So it seems to work. So how did Janelle come up with her equation? Well, it looks like she did it on accident, right? Looks like she did top over bottom equals top over bottom. So Kamran asked Janelle, will that always work and can we prove it? He drew the figure below. What information should he add to his diagram? What else will he need to prove? I think I need another picture for that. I'll be right back with that picture so that we can do C. So in Kamran's diagram, it's just a generalized triangle with arbitrary lengths A, B, C, and D. So let's see here. If I split this triangle up and attempt this triangle, let's see if we end up with what Janelle came up with. So this would be A and C. If I call this angle A, angle D, and angle E, and then if I call the larger triangle here, I'm going to call them A, B, C. So that's going to be A plus B, and c plus d. Let's go and compare sides here. So we'll write a proportion. A over a plus b is equal to c over c plus d. I'll go and cross multiply and get a parentheses c plus d is equal to c parentheses a plus b. And so what I'm going to do is I'm going to go and distribute, and I'm going to get AC plus AD is equal to AC plus BC. Well, notice the ACs are going to cancel each other out. So I end up with AD is equal to BC. So now if I divide both sides by D, I'm going to get A equals BC over D. And if I divide both sides by b, in other words, multiply by 1 over b, I get a over b equals c over d. So actually, Janelle's version does work as long as you are dealing with this side splitter scenario. And this side splitter scenario that I'm talking about is going to be defined in our conditional statement. And you will get this in a resource page. So it basically, so the side splitter theorem basically says if a segment intersects two sides, move that over, two sides of a triangle and is parallel to the third side of the triangle, then the lengths of the parts are proportional. Which basically means A over B is equal to C over D. Okay, go ahead and pause for a second. If you need to write that down, I'll move on to the next problem. All right, we're on 2-11, and we're basically being asked to write the converse of the side splitter theorem. So remember, the converse of the statement switches the if-then portions. So this time we're going to say if a segment intersects two sides of a triangle so that the lengths of the parts are proportional. In other words, that's the whole A over B equals C over D part. I'll write that down. Then the segment is parallel to the third side of the triangle. So there's our converse statement there. Again, that's the proportional part, A over B equals C over D. Give me a second. I'll go ahead and get part B going. Part B reads, the hypothesis or the if part of the if-then statement can tells you what you can use as given information in your proof. What can you write from the given information? Well, remember, this is the whole A over B equals C over D part, right? So this is the proportionality part, the if part of the if-then statement. And it says, are the triangles in part C, are the triangles, are there similar triangles in the figure at the right? And so if so, write a similarity statement and justify your conclusion using a similarity triangles condition. So let's see. If we know that A over B equals C over D, then we know that A over A plus B is equal to C over C plus D, right, based on the proof we did in the last problem in part E. Which means, so therefore, MS over MV, in other words, the small over the large, is going to be equal to MN over MT. Again, that proportionality right there. So what we have is we can say then that the triangles are similar by side angle side, right? Because this angle M in between is the angle in between the sides. Let's go to part D real quick. The last thing they're asking us to do is to prove, that the two lines VT and SN are parallel. So how do I do that? Well, we know that if triangle MSN is similar to triangle MVT, then the angles, angle N, will be congruent to angle T by corresponding angles. by corresponding angles. And if the corresponding angles are congruent, then we can say, therefore, VT is parallel to SN by corresponding angles being congruent, therefore the lines are parallel. Okay, that'll just about wrap it up for this similarity portion of the lesson. As always, leave questions or comments in the comments area, and I will see you in the next lesson.